And yeah, we'll move on to the next speaker, which is me. So I'm Wesley Harrison. I don't think I introduced myself really in the beginning, but yes. So I thought we'd just change gears because I know we've got another good cavity talk coming after this, but I thought let's throw something in where geophysics is being used to solve another engineering problem, but it's quite different from the talks we've given today. So I'll be looking at advancing track safety using geophysical methods. So first, what is the problem we're trying to solve and how does geophysics fit into it? So the problem is essentially we have two major engineering layers beneath the rail network. One is called the ballast and one is called the subgrade. So the ballast is basically those rock chips that you see the sleepers settle in. That's essentially the suspension of the train. And if those start to deteriorate or clay up, become more silty, it loses the suspension quality of the ballast, and it can't spread the load as much above the subgrade layer. This will result in sort of a deformation of the rail itself. So you start getting like wavy rails. And at the end of the day, it does cause derailment. So it's quite a major problem. The second deeper layer is called the subgrade. So this is another engineered layer. This is quite a competent layer. It's meant to hold the heavy axial loads of the rail. If we do have issues with this layer, so it starts degrading, we start getting deformation of the rail again, which no matter how good the ballast is, if that starts deforming, then we have major derailments. And even on a minor scale, it actually makes the train ride uncomfortable and causes wear and tear on the trains themselves. So that's the problem that we are facing, that we're trying to apply some geophysics method to just see, can we understand these layers better for maintenance purposes? So traditionally, what tends to happen is we put test pits out every 5 to 10 kilometers. And that's basically what is used to see how healthy the rail system is. The problem with that is, as we know, a test pit is a 1D measurement, and it's about 2 meters deep, which is really where we're trying to look at, is that international standards for railways have tightened up quite a bit, where the standard requirement requires less than 10 millimeter undulation in that subgrade contact over a 10-meter period, like a 10-meter segment. How are you going to ascertain that from that kind of data frequency along the rail? So that's the first attempt at solving it, but now we need to think of a way to improve this kind of understanding of the rail. So we need something that is pretty high frequency, is a shallow technique, a pretty easy technique, and that can be used quickly on a railway line. So we can't do things like MASW while the trains are going by. So we need something that will actually assist with this. So naturally, I think everyone knows GPR is a very shallow, high frequency technique. And what we've done here is we've developed a system that has 3 antennas. So you have your 3 major antennas, which are shown here. So this is left of the rail, center of the rail, and to the right of the rail. These are both 400 and 900 megahertz antennas. And then we've got a horn antenna, which is 2 gigahertz. So this is a great system because it can measure data at a frequency of about, I would say about, if we're going really slow, 3 millimeters. That would be the resolution laterally as we go along, up to about 20 millimeters. I'll just say conservatively, we get a data point every 20 millimeters on the track. So it's a pretty high resolution, almost continuous data set that we can now use to link up these test bits. So great, we have a geophysics method that we can use again to link traditional engineering methods together and provide a more holistic product for the client. The next problem, okay, so if we get the data, what do we do with it? Because we still have to process the GPR data. It's easy enough to collect, and we can modify the system. But we had to look around once we had the system going, and there are only 1 or 2 major rail ballast monitoring companies on the planet. They're pretty much a monopoly because that's all they do, and it's pretty hard to get anything from them. If you do want to use their software, they actually, right now, they prefer you not to use it. They would like to actually do the work and then do the interpretation. But if you are lucky enough to get a quote from them, the software license will range between 500,000 to 2 million rand, depending on the different modules you want and all their fancy like interpretative stuff. And there's no flexibility. So if you want a different pie chart, for example, they're going to charge you for that. So there's no way as scientists and engineers like testing these geophysical methods to change something quickly and see if it will improve the actual outputs. So what we decided to do as the geophysics team at SRK was we'll give it a crack at creating our own code and at least at some level replicate what's already been done and then improve on it to see if we can create a more holistic sort of product at the end of the day. So what's cool about this is on the right is a sort of a theoretical wiggle from a GPR signal. So the gray is the ballast, so that's that rock layer at the top. So you have a major reflector at the air ballast interface. The second largest reflector is at the ballast subgrade interface, and then the third largest reflector is between the subgrade and then the natural formation material below. So it's a pretty simple sort of signal that we're trying to look and pick and use as analysis. And we get very similar signal from our actual data from the system. So we're definitely on the right track and our system's working. We're getting the data. So it allows us to actually now hopefully pick the data and create some sort of product that is useful to look at the maintenance of the rail system. The next problem is that the raw data is obviously dominated by the airwave. So its amplitude is pretty high, so it's hard to see anything else. The other problem with the GPR data is that the actual sleepers cause noise in the data, which most GPR programs tend not to have in the processing. So we had to develop that, and because it's all proprietary from other pieces of software. But at the end of the day, once we process the data, we get a radargram that looks like this. So you can actually pick the reflector of the ballast and the subgrade, yeah. And that's ideally what we need and what we want to collect along the rail so that we can understand how healthy the rail is along a large section of the railway's data. So we actually start with two processing flows. The one is a less processed GPR data set where it's quite quick to process. We basically look for anomalies like hyperbolas, which are related to infrastructure or possibly cavities or even edges of anomalies, to things like where the ballast is starting to deteriorate, where we don't have a nice reflector, a nice amplitude, or even sometimes the lithology itself, we tend to see cross-cutting even in the subgrade formation. You get it settling within contact. So those things we actually go through. We pick manually by eye. There's nothing fancy about it, and it's a product we can give quite quickly to the clients and the engineers. So for example, here's a small section of rail that was collected, and we had a look at the data. We picked the data and we had a look at anomalies, and we basically zoned areas out for the rail that showed these different anomalies. Specifically in this case, it was the subgrade that's been the issue on this part of the line. This data was then provided, and what was really interesting is where we picked on the 3 and 10 as you get this wavy nature on the railway line, which is exactly what happens when you have poor subgrade and poor ballast. It starts deforming the actual rail, and this causes a lot of derailment. So it's something that has to be looked at, and it's hard to see in the test pits, this kind of in this kind of volume and spatial data. But with this, we can actually start seeing things more spatially, and because we have so much data, we cover the whole bit of rail. But that's just the quick data processing that we can provide as a quick response to immediate repairs or further investigation. We've also created a whole processing scheme and classification scheme that we've had a look at in terms of literature and then some of the new work that we've done. So at the top, you can just see this is the picked layer. So all we do is a radargram. We look where the ballast reflector is. We pick that, just like in seismics, as well as the subgrade reflector. We create a few nice products that can be used quickly, like the ballast thickness and engineering layer thickness. So these dotted lines are basically prerequisite thicknesses needed for the engineering layer. So it can be actually seen quickly where there might be a lack of ballast material or where the subgrade might be too thin. And then additionally, we create these detailed classifications. So what these are, they're basically, for example, the GBF, which is the fouling index, looks at the undulation of the ballast reflector as well as its amplitude. So how weak its amplitude is relative to the rest of the data. And that's used to classify how much fouling is possibly within that ballast section of rail. Additionally, we have a moisture index, which just looks at the possible moisture, the amount of moisture within the ballast. These two classifications get put together in a summary classification called the ballast index, which is just taking the worst classification from these two and then just reassigning them to the ballast index, which is given as very good, moderate, and poor. That's just a nice way to have a look at the data in summary form. We also have the last two, which is the surface indexes for the ballast and engineering surface. This again looks at the undulation at about a 20 millimeter interval. And again, it shows you sort of the health of the rail on that level, with the formation index, where we summarize those two, taking the worst index of both of them. We have a new index called the subgrade undulation index, which is essentially that new standard where you can't have more than 10 millimeters of undulation on the subgrade. And yeah, our tracks aren't looking that great, but that's what we've implemented now. And it's now also important to understand where we've improved a lot is the test bits that are collected are integrated into the processing flow. We have a variable velocity model to change the two-way travel time to a depth, and that's where the test bits are used to calibrate this. So it is calibrated with engineering data, so we can have some consistency and basic. We have confidence in these steps. We also create some summary data sets for the different runs, just so that the engineers can just have a quick look at the health of that section of rail quickly. So with the current system, we do about 5 kilometer runs, but these are done concurrently. So each 5 kilometer run will get a summary classification, and then at the end, you get quite a big summary classification. But this can be customized. Like I was saying, the guys wanted pie charts for this kind of product, but you can do histograms, bar charts, anything. That's what's nice about having our own local sort of technology to work on. We also actually provide the raw data, so the classified data from the GPR to the clients as a CSV file. Unfortunately, these are really massive data files because we have a data point every 20 millimeters. So it's hard for the clients to use this. And that's where, as geophysicists, we have to understand we can't just give these big data sets to engineers and expect them to use them. And you need to make it a bit more palatable and useful for them in their software or in their strategy. So that's something to think about in the future. So what we've done is created a dashboard. It's still very much a work in progress. But what it really does, it subsets the data depending on the sort of spatial resolution that the engineers want to work at. So for example, 10 meters, they're not going to change a 10 millimeter section of rail. So, that 20 millimeter resolution, although it's great, you need to make it a bit more practical for the engineers. So by this, we created a dashboard where they don't even need a GIS system. They can actually go in, choose different areas or different indices, and actually select the areas and export a KMZ or a GPS file, and they can go directly to those areas to check where on the rail that we have these problems. And from there, they can work out a practical strategy for the rail monitoring. Just some additional stuff which has been interesting is, besides the radar, it was interesting to see where we have some really large reflectors that are affecting the ballast and the subgrade. They tend to match up with big contacts in the magnetic data, regional mag data. So it's again important, not just the GPR data, but include things like magnetic data and gravity data to see where these contacts are and how they could be possibly affecting the rail itself. Additionally, we want to include INSAR on areas that are problematic to look at how long there's been deformation in those areas, and to maybe have a bit of a forensic analysis on it. So this will be something that's included as part of future products for the railway monitoring. Additionally, just to look in the future, so this is applied to railways, but it's a GPR system, and you can put as many antennas as you want. We're planning to put thermal, infrared type systems as well as LiDAR on the actual system itself. And there are many other uses for GPR, which everyone would know. So one of them was looking at haulage roads in open pits, basically look at the health of these roads and how they are behaving over time. So you could run this, you could just add the system to a truck or a bakkie and just have it go through the open pits and just see the health of the roads and see how that changes over time. Additionally, the easiest one would be just to put this on a truck or a bus and just run it on the national roads and do preemptive maintenance where the roads are starting to degrade instead of just actively repairing roads. So this is something looking into the future that this technology could be applied to. But yeah, that's it from me. Any questions?
Wesley, it may have escaped me, but on your radar along the railroad tracks,
Yeah.
were the actual GPAR antenna mounted on a bogie, which is running along the railroad tracks, or behind a truck on a road alongside the railroad tracks?
I think it was in behind. I'm just confirm with Rian, but I think it was behind. So we have the three main antennas, which are the main source, and then we have the horn antenna that sits about 2 meters in front of the system that collects the 2 gigahertz data.
Okay, I can accept that, but the question is still, were the radar antenna poised directly over the railroad track?
Yeah, so they're sitting. So you have the two railway lines. So the
Yeah.
one sitting in the middle of the two metal, and then on either side. So they're not on the metal rails. They're on either sides, and one's in the middle of the rail. So that's why we get the sleeper noise as we go through, and that's what you have to process out. Otherwise, you can't pick anything. So that's how the antennas are orientated.
Don't you have any ringing from the metal rails?
Yeah, we do have a little bit. So we're working on processing that. So the current system has slightly older antennas. So we're looking to get new ones and possibly better ones. It's very much a proof of concept. I mean, it does work because the Europeans, this is what they use to maintain their rails. But,
Yeah.
to get a European company to do our railway line, it's literally 10x the cost that we can do it. So it's just trying to get local capacity. But the big thing is to upgrade the antennas, because the 900 megahertz antennas they get quite noisy. So they're almost useless in terms of picking the data, where the 400 gets a bit deeper. So that's the main one that we use to pick the reflectors. But it'll be cool to add additional antennas further off from the array to get a more 3D understanding of it. Because now if it tilts, it's hard to tell, geometry wise. So that's why LiDAR and thermal will be included in the next iteration of this thing. Yeah.
Okay, thank you.
Awesome. Thanks, Jeff.